Hey everyone, today we're going to talk about curve fitting with polynomial models. So some of this stuff will be pretty familiar because we did this with quadratic models, but it's going to change slightly because we're going to be talking about higher order polynomial functions. So make sure you have your calculator handy before we get started, so pause the video if you have to go find your calculator. Okay, so the first thing we're going to do is if we're given a table, we want to determine what the degree of the polynomial would be that best describes the data in the table. So we did this when we talked about quadratic. Remember, we had to do the second difference, and if that second difference was constant, then it was quadratic. So we're just taking that same idea and taking it a step further. Remember, the first thing we have to check for is that, excuse me, is that our x values are constant, the difference in our x values, which it is here, right? This is a difference of 3, this is a difference of 3, and all of these have a constant difference of 3. So we know that we're good there. If that wasn't a constant difference, then it wouldn't model anything specifically with that data. But because it is constant, then we can go down and look at the y values. And we're going to keep taking the difference until we get to something that's constant. And once we get to that, that will determine the degree of the polynomial that we have. So if we go ahead and take this first difference, we'll have 20 here, and then we have 6, and then we have 0, and then we have 2, and then we have 12. So that's our first difference. Our first difference. Our second difference would be 14, and then 6, and then 2, and then 10. So clearly it's not constant, so I have to go on to my third difference and see if I get constant from there. If I take my difference here, I have 8, and then I have 4, and then I have 8. And if I go down to my fourth difference, I then have 4 and 4. And so I can say, okay, well, now that my difference is constant, I'm down to the fourth, so I have a fourth degree polynomial. Now, in your book, it gives specific names for those. It calls it a quartic. Third degree is cubic. I'm not really worried about those names. You can just keep it as fourth degree or third degree or fifth degree or whatever it happens to be there. Sometimes the data is laid out this way, sometimes it's laid out more vertically. The process is still exactly the same. You're just going to go through and do the same thing. So if I'm finding the difference, I have -5, -2, 8, I'm sorry, +2, that's a positive there, +2, then 8, and then 13, and then 17, then I have 7, 6, 5, and 4, and then I have 1, 1, and 1. This was my first difference, this was my second, and this was my third, and so this is a third degree polynomial. So pretty straightforward with that part of it. The next part is actually taking the data, figuring out what degree polynomial it would be, and then finding an equation for the polynomial. So here's where you're going to need your graphing calculator. The first thing that we want to do is to make sure that our data is we can find the difference, and to do that we need to make sure that our change in our x is constant, and in this case it is. Our difference in all of our x's is 10. You can tell by looking at that, which means we can go down to these population values and find what that what level we get at that, where we get that constant difference. If I take the difference here, I end up with 1158, 1054, 1655, 2984. I did all these ahead of time. Or I could just let you think that I'm doing this math this quickly in my head. I actually worked them out ahead of time. Okay, so those were those differences there. Now if I go again, so that would be my first difference. Now I'm at my second difference. So if I take the difference of these two, I get negative 104. The difference here is 601. Here is 1329. And here is 2071. Clearly not constant. Let's go down to the third. Our third difference, here we get 705. Here we get 728. And here we get 742. So it's not exactly constant, but it's pretty close. And because we're dealing with actual data where this up here was not really actual data, it was just a series of values. This is actual data. Because it's really, really close, it might not be exact, but it's close enough that we can call this a third degree polynomial. Third degree is going to be cubic. And so with that, we're going to go ahead and put this information into our calculator. Okay, so if you go to Stat and then you press Enter on Edit, you'll see all of the values. You're going to be putting all of these values into your calculator. Now, something to be aware of. If you'll see here in L2, I have all of my Y values. In L1, though, I'm not going to go and put 1950, 1960, 1970. I'm not going to put those values in because that's going to actually skew our data, and it's not going to give us the equation that we need. When you're dealing with years, or pretty much anything for that matter, you want to call this first one 0. And because these increase, then you would call this is 10 away from that, then this one is 20 away from that, then this is 30, then this is 40, and then this is 50. So those are the values you're going to put in your X column. Think about a scatter plot. Right? When you draw a scatter plot, you want to start here. This would be year 0. And then the next one is 10 years after that. The next one is 20 years after that. So that's how we're going to label those values in our calculator. So I'm going to put in 0, 10, 20, 30, 40, and 50. Okay, so I have all of my data in my calculator. Now we want the calculator to do that regression for us, or to do that line of best fit if we were to plot this data. You're going to go over to Calc. Remember, we said this was a third degree, which is the same as cubic. So quad reg would be second degree, cubic regression would be third degree, quart or quartic regression would be fourth degree. And that's how you can differentiate between those. We're going to use third degree, so I'm going to go down to option 6. If you press Enter, and I know I usually tell you put in L1 and L2. If you put it in, that's totally fine. If you don't put it in, it should work as long as you don't have data in any other of the lists. It's always going to default to list 1 and list 2, so you should be fine there. You can see here that this R squared value is really, really, really close to 1. Closer that is to 1, the closer your data is to being exact a cubic function. The closer those data points are to being on the line of this particular function. And so this function then, we can just take it from the calculator, would be f of x is equal to 0.12 x to the third. I just have to pull it out of the calculator. Minus 4.21 x squared. So minus 4.21 x squared. Let's see. Plus 146.37 x. Plus 146.37 x. Plus 2851.64. Plus 2861.64. I think that's what it was. Yep. Oh, 2851. So all I did was took all of those values right out of the calculator. You see they were labeled A, B, C, and D in the calculator. And you can see those correspond with A is the coefficient for x cubed, B is the coefficient for x squared, C is the coefficient for x, and then D is your constant term. So all I did was populate that into the function there. We'll do one more example. In this example, you'll see that the years don't go up in the same increments, right? The last one here, they went up by 10 years each time, so we were allowed to go ahead and figure out the model by doing the differences. Here we can't do that because these aren't going up in constant amounts. There isn't a constant difference here. So we can't use that method. So what we have to do is put this in the calculator to figure out which is the best model to use because we can't tell by doing the differences. So when you put the data in your calculator, I'm going to go over Stat, Edit, and then Clear, Enter, and clear that, and Enter. And we're going to go ahead and put this data into our calculator. I'm actually going to pause the video there, stop the video, and I'll finish it up in the next video. Okay, so stay tuned.